So here's an example from the same things, a blow up, showing contour intervals in the middle diagram and the representation of the DEM with the contour line superimposed on top of it so you can see the differences between vector and raster data. Again, vector data is much more truthful, accurate, and precise if it's done right. The DEM is always going to be coarser and rougher and not do as good of a job as just describing things like the landscape. Your particular research application or project you're trying to solve may require one or the other. They both do an acceptable job of describing the surface. The raster-based version you can do more things with probably than the contour-based version in terms of analysis. But anyway, so here's just showing us using a contour interval, in this case of 50, between the lines, how that elevation is changing, and comparing the two. So maybe if you really weren't sure how to read one of the other DEMs or contour lines for describing landscapes, hopefully this will make that a little clearer to you by associating these contour values describing that part of a mountain, the ridge around the volcanic area that got blasted away, the blast zone of Mount St. Helens, how that changes from a ridge going down into the depression. Here's an example with some higher resolution outputs. And what we're seeing there in the middle, it should be obvious now, it's a tin, right? So we've got DEM, we've got contour lines, isoplus, and then a tin showing us the same location. The tin happens to be blown up for detail, but here you should really be able to make out how the tin is describing the landscape by incorporating elevation, slope, and aspect in those facets simultaneously on the landscape. So anyway, I don't know if it's not very clear. I'm not sure how to help you with that thing, but other than think about maybe a wood carving. If you did a wood carving of a landscape, and each cut from your sharp tool, knife or axe or whatever it was, leaves behind this facet that's describing the landscape. Tins are really, really good at being visualization techniques for the configuration of terrain. Contours are expedient, and they were a way to do things in the past that still work very well if you know how to read them. DEMs tend to be a little bit more difficult to read, but if you get familiar with how they work, then you can mentally kind of imagine what the terrain looks like, and it's probably not going to be as detailed as what the tin is showing you, but you can do a pretty good job using a DEM to visualize things. Any of these three are great ways to look at terrain and elevation changes over time, describing different features on the landscape. The contour version is going to be better at certain things. DEM is going to be better at certain things. The tin is really handy for visualization. And here's with a tin with a rougher set of facets describing the same area. So the first one had a lot more detail to it. This one has less detail. It's still describing the landscape. It's looking chunkier. It's not as nice, not as refined. And now, if we were to do the same sorts of things, looking at a DEM, the contour lines, a tin, and now it's a tin shown in 3D with the contour lines draped on top of it. So it's trying to show us this ridge area as a three-dimensional visualization on your two-dimensional screen, with the contour lines kind of floating a little bit above the surface, showing us the configuration of the landscape by the tin and then those elevation changes and how the contour lines are, uh, how they're displayed and drawn, are trying to describe the same landscape, and just in elevation change and in somewhat the shape. So contours are another type of a surface. Here we're looking at isolines, isopleths as that surface. And how you create them is from a DEM. You open up Spatial Analyst Tools, look under the Surface Toolbox or drawer, and find your contour tool, and then apply that to a DEM and generate contours at whatever contour interval you prefer. They're really easy to create, so that's how you do that. We're going to look at a couple of other things in general about terrain analysis, things that we don't go into very deeply in this class at all, but a couple of other tool sets you should be aware of. There's a hydrology tool set, and which consists of surface hydrology, and there's also some groundwater hydrology tools built into ARC. Those are things that get examined in more detail in another class, 424, 524, offered through the geography department. But what hydrology is doing is taking information from DEMs and using it to model the flow of water across the landscape, or if it's groundwater, through whatever the groundwater constituents are, the rock types, soil types, and things like that. But here we're looking at the surface tools for hydrology. In basin analysis, looking at calculating flow direction, how much accumulation is going to occur with a rain event, things like that. So here we're getting into more complex modeling involving hydrology and hydrologic techniques, but it's built into ArcGIS and very commonly used by researchers and project managers that are interested in understanding water flow and trying to predict what will happen. For example, if we get a major storm in an area, where's the water going to pool? Where are we going to be at risk for flooding? Things like that. Those types of things you might run through these kind of analyses to get a better handle on how the terrain is going to influence the impacts on the natural environment and the human-built environment, given a sudden influx or a very long-term influx of rainfall. So here, since this is something that a lot of people wind up needing in their careers, I'm going to go into it just a little bit more. Over on the upper left, we've got 3 little DEMs showing different features that we might find in the literature: the pits, peaks, and saddles. Examples of different features, and you can see here that how that grid thing works on a micro scale. With just a 3x3 neighborhood, we can get geomorphic features in there. They're going to look a little bit more complex if we used a tin, and we can't use a tin in hydrologic analysis. We're using DEMs for that. Just to the right of that is another depiction showing the landscape, and it's showing different things that are happening on the landscape at points C, B, and A. C is a ridge, so water will flow to the right or the left off the ridge. B is like the valley bottom, and so water is accumulating there from both sides. Then A is a slope, just feeding down into that. So, thinking about a DEM and generating these other surfaces off of it. Here's a surface that's we're looking at how the water is going to flow based on the elevation values. Okay, where is it going to go? How much is going to accumulate down at point B? If it's raining across this landscape and it drops an inch of rain, what can we expect to happen down at B? That's the kind of things that hydrologic analysis are going to be interested in. Down on the left-hand corner, We've got another version of a DEM showing different values, flow directions, the drainage network of different streams or rivers that would accumulate on the landscape and flow, carrying the water in them away from where the water fell on the cells. So going from higher elevation to lower elevation areas. The arrows are showing flow direction, and the numbers attached to them are showing the compass direction or the aspect of that flow. There we don't see how steep the terrain is. We don't have any indication of what the slope is. Over on the right, on the far right, we've got a sequence of diagrams where we take elevation as an input, flow direction aspect as an input, the accumulation of the amount of water that falls on the landscape and gets pooled and then travels together as a unit, flowing down either as sheet flow across the surface or collecting into a stream. And then the stream network itself, where we're developing streams, down at the bottom, we're doing a watershed analysis. So we're putting all these different inputs into an analytical procedure. Then we can look at an entire drainage basin at whatever scale we're interested in, and then do a lot of computations and calculations, predictions about what might happen in that particular basin given a particular amount of annual snowfall, given a particular storm event that drops a hypothetical amount of rainfall on the area, those kind of things. Trying to get a handle on managing water resources is what the hydrologic tools are all about. And we live in the western states and the Pacific Northwest. This is something that's very important. Trying to get a handle on what's happening, knowing that climate change appears to be happening, and snow appears to be a little bit more variable. Water, therefore, is a little bit more variable. When people depend on water, it's really handy to be able to predict, the amount that you're going to get throughout the years. And this is where those analyses come in trying to inform water management systems at the government level. Another type of terrain analysis that we're actually not going to explore in the class at all, but something that I'm going to mention. That's a really good example of something a little bit more complex we can do with our raster data model, is modeling solar radiation inputs. So the sun is always putting out radiation in all directions. The Earth intercepts a certain small fraction of that on any given day, depending on cloud conditions and a bunch of other atmospheric conditions and surface conditions and all that stuff that you probably would have learned about in an introductory physical geography class or some other course. In GIS, we can take the DEM and then feed in a little bit of information about atmospheric conditions and calculate how much radiation a particular cell receives based upon its landscape configuration. And that's what these diagrams are trying to demonstrate. On the left is the sun. It's an image from the SOHO satellite, the Solar and Heliospheric Observatory, in a particular wavelength. And so we can see the sun in all its nice fury, very active, generating radiation, sending that out into space. We intercept that at Earth on the right-hand side, and we have radiation that, what it's trying to show is 3 different pathways for radiation for a cell, where it's direct from the sun to that cell, nothing in between. There's no intervening barriers or modifiers. The cell can accumulate reflected radiation from other cell locations, depending on the landscape, or maybe it's icy, maybe it's some more reflective rock than an absorbing rock structure. So radiation gets reflected, and it still accumulates at that cell. And clouds and other atmospheric constituents can intercept the radiation and also reflect it. That's what we call diffuse radiation. So the accumulation of direct, reflected, and diffuse radiation tells us how much solar radiation that one cell receives in any given specified period of time. So what this tool does, the solar analyst tool built into ArcGIS, it's going to look at each individual cell. So down on the bottom, the 3 diagrams down there, it's going to look at each cell and say, what is its configuration related to everything around it? What does the sky generally look like around it? So that what we're seeing there in the middle and the right, or if we put a special kind of a lens in a location and looked up at the sky, what Solar Analyst is doing, the solar radiation modeler, is it's saying, all right, what's the terrain look like around me? How is that going to influence how much radiation I get? Where is the sun in the sky? And at different times of the year, the sun is going to be at a different angle above the horizon. So altogether, how much radiation is this cell going to receive? And then the output becomes that measurement in like watts per square meter. So here's an example just to show you a little bit of what happens there. We have a DEM over on the left, 3 or 4 different sample locations across the landscape. So we're trying to find the proper location or best location for a new solar panel array on the landscape. Where would we look if we didn't have a clue about the best place necessarily offhand? We'll do an analysis and try to figure it out, or maybe our project requires us to do an analysis for this particular reason. So we run the DEM through the Solar Analyst tool. It does those calculations for us for a given amount of time. Sample points 1, 2, 3, and 4 are shown below on that screenshot of a table. And so the output, T0, probably looking at whatever that means, some measurement of time. Cell location 3 has the highest value, and what that it means in this case, we don't know offhand what the units are, but the highest reading in that column indicates that position number 3 is going to be receiving the greatest amount of solar radiation over the time frame of the analysis. Could be a month, could be a year, that could be total annual solar radiation. It might be within a single month. It might be within just the month of July or something like that. That's something we don't know, but the highest value in the output is going to be the best location, the best potential site location for that purpose. So this tool gets used quite a bit around the world when people are trying to figure out, especially now with the higher and higher resolution data that we have, where's the best place to put solar panel arrays to collect solar radiation and convert it to electricity. Okay. So here's just another neat example of solar radiation. It's a tool that I've used in the past on older versions of ArcGIS and very older computers. But the tool that's built in is basically the same algorithms that I used a number of years ago to do this kind of analysis. So I'm pointing it out and highlighting it here. So there we are. Terrain analysis done in different forms, using different data sets to solve different kinds of problems, produce different kinds of information to help people do things, make decisions about projects involving terrain.